Okay, guys, welcome back to the Grimerica Show. Coming at you with video for the first time in, it's got to be at least 3/4 of a year since we gave this up because it's just too much of a pain in the ass. But we did this great show with Simon and Patrik about the Tychos.space model and why the heliocentric model doesn't work. And it was super visual, and we found that during the podcast, I forget the number, it might have been 560. Anyway, during the podcast, we were referring back to the Tychosium and using that, and we got a ton of feedback on the episode. A lot of people liked it, so we figured we'd dust off the cameras and do another video show here where we can have Patrik share it and Simon sort of, both of them, fill us in on it, and it's going to be great. So, first video in a while, enjoy it.
Yeah, I don't have much to add to that, really. I mean, Simon wrote the book, the Tychosium, the Tychos, our geoactual binary solar system, and Patrik made this great 3D model of the representation called the Tychosium. So, I mean, maybe we'll start. Welcome back, guys, and this is going to be exciting, showing this visual representation. Maybe we'll just start with a real sort of high-level overview of why, the difference between this model and our traditional model that everybody thinks is going on up there in our solar system, and then we can jump into the screen share with the Tychosium. You want to start with that, Simon?
Sure. Hello, and thanks for having us back. Can you hear me okay now?
Yep. Yeah, it's good.
Great. So, well, let's start. Let me do a very quick summary of what the Tychos is all about. It's really the system that Tycho Brahe made in the 16th century, but with some important additions which make it work absolutely perfectly, which wasn't the case exactly at the time, because he said that the Earth was completely stationary, and also that it didn't revolve every day. So I have given a diurnal spin to the Earth. Every 24 hours it goes, around itself. I think we can agree with that. And also a little motion, which is the motion it does. But now I have to go to the big part of the whole system, is that our solar system is a binary system. It's composed, the binary pair are the Sun and Mars. And they, in Tycho Brahe's old model, he had their orbits intersecting, which everybody was laughing about. They said, oh, they must crash into each other sooner or later then. But they didn't understand at the time that they didn't know about the existence of binary systems. So what's a binary system? It's simply, we have discovered in the last 20 years that practically all the stars are binary. They are two stars, a big one and a smaller, and they revolve around each other, around their common barycenter. And usually there is nothing in the middle, but in our case, for some reason, the Earth is in the middle of that dance. And the dance is performed by Mars and the Sun and Mars. They dance around in intersecting orbits. And of course, this makes incredibly statistical sense, because we now know that absolutely 100% of the closest stars, at least, that we have around us, they are double. So why would the Sun be the only single guy in the universe, a single star? So that's the main point of the whole concept, because it is absurd to think that the Sun would be the only star that doesn't have a local orbit, which means a small orbit, which it has. It has a 1-year orbit. It goes around us. And all other stars have orbits some have orbits of a few weeks, some have orbits of 3 years, or 12 or 29. But all the stars have small orbits. But they are telling us that the Sun doesn't. They're telling us the Sun has one orbit which lasts for 50 million years around the galaxy. So the Sun wouldn't have its own orbits, according to Copernicus. according to the heliocentric theory, which is in itself absurd, right? So that's the basic thing that we are putting forth. We are a binary system like all the other stars. It makes total sense. And this also explains so many other things, which at the end of my book, I list 36 points which get resolved by the Tycho system, by the Tychos model.
So Mars is a red dwarf then in this instance, and we're kind of situated in between the sun and Mars?
Well, it could be red dwarf. It is reddish. I mean, that's what we see in the telescopes. And all red dwarfs are reddish. And red dwarfs are the absolutely most common stars in the universe. And we know that, and even officially they say that many, many red dwarfs are so dim that they are invisible. So Mars, isn't shining with its own light, and most red dwarfs are not. So why couldn't Mars be a red dwarf? It could be, but let's not, let's not argue about definitions. We need to understand now that theory is right. It's a theory by some researchers who say that all bodies in our system are stars in different stages of their evolution. So even maybe the Earth was, a long time ago, a star. What clue do we have for that? Well, we have magma in the middle of Earth, which sometimes comes out of the volcanoes. So there is something really hot in the middle of Earth, right? So it kind of suggests that maybe Earth was a star as well a long time ago. And I think that the stellar metamorphosis theory is interesting. And we really need to redefine what are planets, what are stars, and what are moons. Mainly, moons are really easy to define, actually, because moons are these objects that go around their hosts and always show the same face to their host. And that's the case of our moon. We always see the same face of our moon. It's like it's a magnet attached on a string, going around Earth. And magnets has power, I guess. And Venus and Mercury, I call them the moons of the sun because they show the same face to the sun. They also show the same face to us, actually. But that's a controversial issue, because for many, many years, all astronomers were saying that Mercury, for instance, and both Mercury and Venus were tidally locked. Tidally locked is the jargon in astronomy just to explain this, that they always show the same face to their host. So Mercury and Venus, if we now, when we'll go to the Tychosium simulator, we'll see that it's kind of obvious that Mercury and Venus are the moons of the sun. They always ever go around the sun in circles, and the moon goes around us. So I call the moon our moon. I call Venus the first moon of the sun, and Venus, I call Mercury the first moon of the sun, and Venus the second moon of the sun.
Good. Well, thanks. Yeah, that's a good overview. I mean, I think that it's important to mention your book is very in-depth. There's many chapters, and there's a lot of information on what backs this up, and also other aspects that sort of are strange in accordance with our normal narrative right now. It just doesn't make sense. So there's a whole bunch of chapters on this, but this is a great visual representation here. Patrik's sharing the Tychosium now, which is at what is it? ts.tychos.space. Yeah, it's fantastic. So we'll go through this now.
Yeah, Patrik has been doing some incredible work these latest weeks with a new version, but this is the one we have now, and this one is already extremely accurate in the sense that you can go anywhere in time. You can go back thousands of years, and you can check them, compare them with official tables, and the planets are where they have been observed, both in right ascension, which means celestial longitude, and declination, which means celestial latitude, and in their distance from Earth. So everything checks out with official tables that have been collected, gathered by the best astronomers for hundreds of years in this simulator. So it's nothing, it's nothing fancy. It's absolutely, it checks out with everything that we have in tables, despite of it being quite different from the idea that we are going around the sun at 107,000 kilometers an hour. That's what they are saying. They're saying that we are going at, that's 90 Mach, that's Mach 90. That's 90 times the speed of sun we are supposed to be doing right now, guys. And I think it's more plausible that we are moving in space much slower. And in the Tychos, we are moving at 1.6 kilometers an hour, which is almost exactly 1 mile per hour. That's the speed, the orbital speed. Now you can, now Patrik can show you what happens over many years, because Earth looks stationary here, but it's actually moving to the right of the screen. So if you put, do this thing, Patrik, maybe.
What's the farther?
Yeah, sure.
For 100 years,
What's the farthest ring right
years.
now? What's the farthest ring out there right now that we can see?
This
This is
Jupiter.
That's Jupiter? Okay.
And then if we zoom out further, we have Saturn, and we also have
Uranus
and Neptune. We haven't brought in Pluto yet, but those are the planets we have. And one thing, and that's also something that works best to show graphically, that's the retrogrades. That's always been a problem within astronomy. How do we explain the retrogrades? And what is the retrograde? Well, it's that sometimes the planets move backwards in relation to us.
Mercury's the one. Mercury does it for sure, right? That's the one everyone always freaks out about.
Yeah.
In relation to the stars, really, in relation to the stars, they look like they suddenly reverse direction. Yeah.
Yeah. So, and we can actually see that because, that what was Tycho Brahe's, what's so brilliant with his model, that was that if you do this configuration where the sun moves around the Earth while the other planets are moving around the sun, the retrogrades, they solve themselves. Because of this motion, the planets will appear to move backwards in relation to this. And you can see it if we put on this trace function. We can see this here with Mars is going into retrograde now. Now it's moving backwards.
Yeah, for 70 days on average, it moves backwards.
Yeah, maybe you can just point out the planets just because they are pretty small. So Earth is right there in the center around where the Berry Center is in the Earth. And
here we have Mars.
Yeah.
And here we have Earth in the middle. Let me center Earth here. And then we have Mars. And I've put the trace on Mars now, so we see how it's moving. And then we have Venus, Mercury, the Sun. And this little gray dot is the so-called barycenter that Earth is moving around.
Well, I would stop you there, Patrik, for a second, because I'm coming to think that the barycenter is Earth, actually, of the system. Because because then that gray dot in the middle is just the middle of the 24,344 year revolution we do. And it's not the barycenter itself. It's just the middle of the whole precession of the entire system, which brings us to do this blue ring, as we can see here.
So when you were showing us earlier, now that wasn't part of this episode yet, but when you showed us the sun centered around the sun in the great year, that would be around a one rotation around the barycenter then?
Yes, I mean, the barycenter remains Earth all the time. But for some reason, the whole system also goes clockwise once every 25,000 years. And that reason, that's also a new line of thought I've come to in the last few months, is because our system is going around the Sirius system, which is the brightest star in the sky. And therefore, we kind of make also another motion, rotational motion. The whole system makes a rotational because it goes around another system, which is the Sirius system, composed by Sirius A and Sirius B, which incidentally are proportionally identical to Mars and the Sun. Sirius A is 205 times bigger than Sirius B, and the Sun is 205 times larger than Mars. Now, don't ask me why this is, but that's the fact.
That's diameter, not mass?
The diameter. We're talking about the diameters, of course.
Do you know what about the masses?
Well, that's the big question, The masses, they had when they discovered Sirius B in the late 19th century, they were absolutely, there was panic because they said, how come this little thing, Sirius B, rotate around this huge thing? And that doesn't make sense, and we have to revise all the Newtonian theories then. But then they came up with this excuse or incredible ad hoc idea that the matter that composes Sirius B is extremely dense. It's 400,000 times denser than the atoms on Earth. And therefore, Sirius B is very small, but it's extremely heavy. That's how they save the face, But who has put Sirius B on a bathroom scale and seen if it's that heavy, or Sirius A? Who has ever done that? That's just conjectures. That's just fantasy that astronomers are going on about. That and it goes exactly against what Newton was saying. Newton was saying that physics are the same all over the universe. That he became famous for saying that. But in this case, if Sirius B is 400,000 times denser than any other place in the Earth, it completely destroys the beautiful Newtonian theories.
Yeah, there's so much. What do you say, Simon? Shall we try to explain with Tychosium the PVP orbit and its significance and how it explains the precession?
Sure.
What's the PVP orbit again?
Yeah, the PVP orbit is what Simon has named Earth's slow orbit around something. We used to call it the barycenter, but now I don't know. But it has an orbit. Earth has an orbit on its own, but it's the center of the solar system. So everything follows the Earth while it's moving very slowly,
but
1 mile per hour.
Before we do that, can I just ask a quick question about your tracing of Mars? Because if we continue this around, does this show a visual representation of the problem that Copernicus that had with Mars for years, and how there's still that mystery of Mars every seventh time it changes?
Yeah, it was actually captured. Go ahead, Simon.
Yeah, we'll get to that. I just want Patrik maybe to explain a PVP orbit, which was the question that Graham had before.
Darren asked that. Yeah.
PVP means Polaris Vega Polaris. Because now, today, in our epoch, our North Star is Polaris, okay? It's our northern star. We are lying under that star right now, okay? So if you can put your, if you can show that, Patrik.
Let me show you. If now I have turn on the stars, and that is something people need to know, that there is a lot hidden here under the menus. You can actually turn on the stars and have the stars displayed in the model, and you can turn on the star names. We don't have them on by default because it gets very, what's it called?
Crowded. Gets crowded.
Yeah. And I'm working on that in a new version. So you just hover the star and you can see its name, but I've done it this way. So if we put on a helper line, that is a line intersecting the poles, and then we start looking along this line, and what do we see? There we see Polaris.
That's our northern star right now. Okay. You see, it has been for the last 100 years, but the northern stars change over time. Everyone knows that. And what has been calculated that in about 12,000 years or so will be under Vega, which is on the opposite side of the PVP orbit. So that's why I call it the PVP orbit. We go from Polaris to Vega and back to Polaris. Maybe you can show Vega. Can you find Vega here on this provisional star map? It's a provisional star map we have.
Yeah, we are working on improving this, but where do we find Vega?
How does the current model explain why we only see a wobble in the stars every 25,000 years, as opposed to over the course of a year when the Earth should, be traveling? Should be, 93 million times 2 would be 186 million miles away from where we are right now. In 6 months, we should be 160 million miles away from where we are.
Yeah, that's
right
a big
now.
problem. That's a huge problem. And this fact that we every 6 months we would be moving sideways by I'm talking kilometers, so it's like 300,000 kilometers sideways. And in spite of that, we can see, we can't see any big difference, and we can actually see Mars aligning with the same star over a 6 months period, and that is explained in my book. It's illustrated very clearly that it's an impossible. It's absolutely impossible geometrically that could happen. So, and that brings us to Graham's other question. What we have, maybe you can switch off the stars now, Patrik, because they are.
Well, I would like to find Vega first, and I got an idea. When should Vega be our North Star? In which date do we need here?
14,000.
14,000. So let's see what happens if we go to year 14,000 here.
Something like 13 or 14, yeah.
That's into the Dune timeline now.
Well, so where am I looking at? Here. And then we should see. Yeah, here we go. Here we have Vega.
Wow.
So that's one way to find it.
Yeah, but you have to align it in a way that's, you have to.
Got to align with the pole, right?
It's pretty tricky how it is now.
Yeah.
But I've checked it, and it checks out. I checked it. Patrik, you need to rotate so that we can see that Vega in this year is under us. Can you rotate it?
How do I need to? Should I look from the upper side or the lower side, or you? Here we're looking from the side.
Mm-hmm.
What you need to explain to me what you want then, Simon?
Yeah. It's all a question of aligning this helper. But there it is. Okay, so you have Vega.
Yeah.
And now it's the orientation of the whole system that you need to just maybe flatten out now and see. But anyway, it doesn't look right now. It doesn't look perfect, but it will be perfect. Vega will be our star in about 12,000 years' time. And then we go back to Polaris. And that's how Copernicus explained this, that we changed our northern star. They say that the Earth wobbles very slowly. It wobbles, the axis of Earth wobbles in the opposite direction of its rotation and its revolution around the sun, which is really incredible physics. Why would it, have a wobble in the opposite rotation? It's like you have a spinning top that's about to fall, and it starts wobbling in the opposite direction of its rotation. It doesn't happen in real life. Instead, the PVP orbit this explains it much more simply. It's because we are physically going around an orbit, which is this one, the blue one.
Yeah.
Can you show that, Simon?
Let's demonstrate
on
this.
The way we did before.
So if I do reset now here, we will go back to the year. Now we are at year 14,000. I do a reset.
Mm-hmm.
And now we are at year 2000. This is the start year of the start date of the Tychosium. So now we have Earth here.
Mm-hmm.
And now I set the stepping factor to 100 years.
Mm-hmm.
So each time I click
1 second, right? So 1 second equals 100 years.
Yeah. So if I start the model, it will just go like this. Now I'm actually looking from it on the upside down. I don't know. Let me do a reload here. It's so I set the factor to 100 years. So if I
by steps only. Just go steps forward.
Yeah. Okay. I do it by steps.
Yeah.
So if I could do a step here, and if I turn off the trace, so
every step now is 100 years every time you click it.
Exactly.
Yes.
So now we are at year 2,300 and moving forward. And you see, Earth is slowly moving like this. So I can and I can increase this even more. I can put it to 1,000 years. So.
Mm-hmm.
So now it'll be 26 clicks to go all the way around that
exactly.
thing.
Yeah.
Yes, Darren. Yeah.
So in about 25,344 years, we will have completed this orbit. And that would be the equivalent to a great year.
Yeah.
That is, the estimation of a great year is that it is around 26,000 years.
Yeah, the official estimation is that, it's like 25,771. But in the Tychos, it's slightly shorter, and I explain it also in the book why it's 1.6% shorter. It's explained very, very carefully, and I have corroborated this exact number of years by so many other methods that I'm really confident that that's the actual time we need to go do one orbit around the system. 25,344.
Patrik, can you put your helper line back in there to Polaris and watch it go that way?
Yeah. So first I do a reset here. So we go back to the year 2000. And then I go here and I put on the polar line. And I extend it to its maximum length. And then I put on the stars and the star names so we can see that it's the... And now I'm looking from underneath the Earth. So I'm looking up along this line. So I'm now looking below our system. And you see, here we have Polaris. So if I start stepping here, let's do 10 years. And now I'll step forward. We will see our northern axis will move across the skies. So now still Polaris is our northern star. But but when I move forward, it will eventually zoom out. So now we are in year 2350. And then
Now you have it upside down, right? So it's a bit confusing.
Yeah. No, it's not confusing, Simon. It's the only way to show Polaris like this.
Okay.
I can't show Polaris if we're not looking up along the northern axis. We're looking up.
Bring the stars closer, maybe, and that's.
Yeah, maybe I can do that. Let's see.
But yes, I've been checking it, and it works quite fine. And
so. What's so genius about this is that, I mean, this PVP orbit, it explains the precession.
Precession is the motion of Earth, simply. It's the motion around its orbit. It's no wobble, nothing. Earth is always inclined almost in the same manner, in about 23.5 degrees. Maybe it changes a little over time, but it always stays inclined in the same manner, and it explains also what that question that Graham made before, how Mars can, because what is observed is that Mars will align with a given star. Let's say that you walk out in your garden and you see Mars in front of a star. Okay, we call it the star X. Okay, so star X will return. Mars will return in front of star X in 707 days. Usually,
that's a good way to put it. Yeah.
Then again 707 days, and again it comes in front of star X, and this will happen 7 times 707 days. But the 8th time, star X will appear behind Mars in only 546 days. And you know, how will that happen in the Copernican system, which says that we are in the 3rd lane around the sun and Mars is on the 4th lane? We should always, meet up in the same manner. But this happens because of the spirographic long-term motion of Mars, which you can now show, Patrik, by going fast with the tracer of Mars. And so we can see it's, a fast, maybe put it on a month and accelerate it. 1 second is a month.
Yeah, just so everybody knows, there's different. So 1 second can equal a minute, a month, a week, 10 years, a year. Yeah. So you can play around with all these different speeds.
All kinds of options. And I like to look at it with 1 month and then accelerate it. Yeah. Start
1 month, yeah. So I put on trace here, and it's default on Mars, but you can trace all the other planets as well. But Mars is checked the default, but we can trace Venus and Mercury as well. So, and I start the model or the Tychosium, and it starts drawing. And these loops, retrogrades, is what Mars observably do.
Right there, right? Yeah.
Right there, it goes backwards. Yeah. But it doesn't
zoom in a little bit. Yeah.
It's nothing magic. It's just geometrics. It's gyrational geometrics. Mars is always going in a circle around the sun. And what will happen is that at some stage this will happen. It will seem to go backwards, but that's because of the geometrics of its dynamics. So there's nothing magical with these loops. It's what will happen if you put a little light on your bicycle wheel and you go forward. You will see that light's doing this trochoid. It's a trochoid motion, trochoidal. Imagine a little light on your bicycle. Your wheel goes around, but the lights attached on the edge of your wheel will actually do these things.
Yeah, it's just a consequence of how Mars and the sun moves in relation to each other when they are moving around us. So, and actually, I'm going to talk about this a bit more further on, but I'm working on a new version of the Tychosium, and one thing that we will introduce there is the possibility to have directional errors on these orbits, because then it becomes easier to see how the planets actually move. So I'll switch over for a brief moment here to the new Tychosium, and we start running this, and we have the same kind of settings here. So I do. Oh, I forgot to put in 1 month there. Okay, let's do one. Oh no, it becomes faster. But if I check this option here, now we see little arrows. And then it becomes easier to see how Mars is actually moving in relation to the sun and how Mercury is moving. And we also have, so if you hover a planet, you will be able to see its name and what it is. So,
All right.
Yeah.
So Mars is always ever going in a circle. It doesn't change. It always goes circularly around the system.
And the line and the timeline for that matches what our observations are for a Martian year?
Yes.
Yeah, that's really one thing that we need to drill in as well, that the Tychosium is observationally accurate. And we have a menu here called positions. And here we have the right ascension and declinations for all the planets. And no, let me finish, Simon.
Please.
And so when I click in run here, you will see all these positions move,
right,
because the planets move in the model.
Yeah.
And these are simple geometrical calculations within this 3D space. So every time we are in every second, every time the model runs, we ask what is the relationship of Venus to the Earth in this point in time, and we recalculate that to right ascension and declination. So this model is observationally and astronomically correct.
It's absolutely correct. I've been checking it for years now. I mean, the Tychosium has been existing for how many years now, Patrik? 4 years, maybe?
Yeah, it's 4 years now. Yeah.
And I've been, spending thousands of hours checking it, and of course, I've also, adjusted it almost by trial and error sometimes, because we really don't know, exactly how far. And slowly but surely, it's become incredibly accurate. And I suggest that anyone who's into astronomy gets familiar with the Tychosium and checks it out, because the accuracy right now is already extremely good, and that is for all the planets that we have in our system. And why don't you show us, for the newbies here of the Tychosium, the beautiful tracing of Venus.
Yes.
So we can see Venus, and maybe go a bit faster, so we can see.
Yeah, sure.
You can use the.
Or maybe we can use the speed modifier here. That's so we can. So this is now we have 1 month, but then we have a speed multiplier, so we can do 2, 1.5, or 2. And we can also use this to go backwards if we want to.
Yeah.
So we removed this because we thought it was confusing, but then a guy told us that no, don't touch that.
He loved
it's one of the most useful things in the.
Yeah, it is. It is.
So now we're having tracing Mars. So let me remove Mars, the Mars goes, and then I put on Venus, and then we will see something very beautiful, and that is the flower of Venus. And this is, I mean, we know that Venus does this from a geocentrical.
But always note that Venus is going all the time in a circle around the sun. It's not doing anything strange, but it will do these backward loops, retrogrades.
It's like a spirograph.
Yeah.
Yeah.
I mean, when I was a kid, I loved the spirograph set. Did you have it when you were kids?
I did. I have it all over my house now because I have kids. So
it was a great thing, you know, all these small wheels, which you could do all kinds of funny patterns with. And you put a pen in the wheel, and when it rotates around another wheel, it will do these things. It's just absolutely natural physics.
And here we can go from we can
still
trace
around the barycenter, or
no, it's around the Earth.
okay.
So this is what.
Yeah.
And then I would like to mention the incredible resonance between Venus and Mars and all the other planets. I mean, Venus and Mars. Venus returns to the same place, closest to Earth, every 8 years. And Mars does so. Mars is in a. Let me try and explain it, maybe from the beginning. I have determined that the Moon is a central drive shaft of all the system, because the average period of the Moon's rotation, as it returns to facing the Sun, which is called the synodic period, is 29.22 days. If you multiply that number by 4, you get Mercury's periods. If you multiply it by 20, you get Venus period. You multiply it by 25, exactly, you get Mars's period. By 150, you get Jupiter, and so on and so forth, up to Neptune. So, you know, how would that be explained in the Copernican model, where the Moon is just a little appendage that goes around us in the third lane? You know, why would the Moon be so important in the Copernican system? But here, it's obvious, because it is placed in the middle of the whole system. So the Moon can be viewed upon as the central drive shaft. I like to call it that way.
And when you speed this up, this exact view that you have here, it almost seems like it's a pump, like you mentioned drive shaft. But if you do like a month or a year at a time, and you see the way it's sort of pumped, it's almost like, to me, it's like a kind of a pump.
Yeah.
Yeah.
Yeah, but
it's
like that,
comes
yeah, right there. You know, it almost reminds me of that Mazda engine, the
rotary engine.
What's that called? The what?
The rotary
Yeah,
engine.
the rotary. Yeah.
Yeah. So here we have
have
all the planets tracing.
Yeah.
And that's because they're all going around the sun.
Yeah, that's
and the
what
sun's
I'm talking
going around
about.
us.
They are all magnetically attached to the sun, probably.
Electromagnetically?
It's a magnetic system. And the absolute accuracy, they are all multiples of the Moon's period, guys. I repeat. Isn't that amazing? And no one has ever said that before. I haven't, you know, that's my conclusion after, because they couldn't say that because they didn't know about the little motion of the Earth and Moon system. So it didn't really match up with what I'm saying. But now that we know, now that the PVP orbit exists, I can say categorically that this is a clockwork. This is a clockwork. Whoever made this was pretty good.
Yeah, that's kind of what I'm getting at. And this really shows it here, the way it's just sort of resonating back and forth.
But of course, you know, you see, the sun is still extremely important in the system. It's not that I have declassified the sun. On the contrary, the sun is really important because all these loops are given by this big star we have. It is big. I don't think it's, I mean,
oh, right.
I've gone with
that's what all the spirals are from the sun. as it's going around the Earth. Okay, I see.
Yeah. It's like they're, to explain it to a child, you could say all the planets are attached by a yo-yo string. All the planets are attached to the sun by a yo-yo string, and that will do that. Or
And then
you
the
could
sun's
say,
attached to us by a separate yo-yo string?
What?
And then the sun's attached to us by a separate yo-yo string?
Well, it's the binary system that is the most important thing. It's the Mars and Sun binary system, which is what we can observe all the stars doing that. They are rotating, they are intersecting, their orbits are intersecting. So that's the main thing, the binary system.
What if we put the stars in right now? What are they going around? Are the stars going around us, or are they going around? Are they moving with the sun?
No, the stars are other binary systems, and they have their own motions. They have their proper motions. They move very, very slowly over the years. And
can we
yes,
go?
By the way, the stars are important because the parallaxes of the stars are explained in the Tychos as well.
Yeah, that's what I wanted to get into, because before we started, Patrik was kind of showing us, why that doesn't work and how the stars were sort of shifting back and forth.
Yeah, please, if I may, let me try to drill in or explain. We all think in different ways, but what really made me understand why a heliocentric model with the sun in the middle isn't very possible, or is not geometrically possible, was this. And if we go to a passage in Simon's book, in the foreword, Tycho Brahe said this in the 7th or the 16th century, or this is a passage about Tycho Brahe. And it says that he further showed that within a heliocentric cosmos, the stars had to be absurdly large, with the smallest star dwarfing even the sun. Various Copernicans responded to this issue of observation and geometry by appealing to the power of God. They argued that giant stars were not absurd because even such giant objects were nothing compared to an infinite God. So they didn't attack Tycho's main argument that the stars had to be absurdly large. And why didn't they do this? Well, because according to the laws of geometry, if you go back to Tychosium and we put back this polar line, and then we start and we go and look at Polaris again, which you have over there. And a thing you can do in this model is to change your frame of reference. Because, what we can observably see, that each year, during a year, the stars stay in the same position in relation to us. If you put a cross here or something pointing to a star, we observe a star at the same time every night, we will see that star in the same position.
That's only and that would only be affected by precession.
Yeah, it will move very, very slightly during decades. The stars will move, but not during the course of a year. We will not detect any motion. So, and this works if we have a model like this with a sun or with the Earth in the center of our solar system. But what happens then? Because in this model, in this Tychosium, you can change the frame of reference. So I can instead of having Earth in the center, I let the camera follow the sun instead and make that the center. So what happens then if I have the stars on and set the sun as frame of reference? Well, then the stars will have to follow Earth around when it goes around the sun. So I mean, the heliocentrism is a very peculiar form of geocentrism, where we say that the entire universe is following the Earth then when it moves around the sun. Because and this is what Tycho Brahe meant, because if we stop this and we look at this, here we have a straight line through the Earth. And if this line should intersect the same object while we're at this side of the sun, and this orbit here needs to be 300 million kilometers. So if this line should intersect the same star when it's here, and if we go around to the other side when it's here, then this object needs to be as wide as this displacement. Two parallel lines, if they are intersecting the same object, then that's the object needs to be as wide as the separation between these lines.
Can that mess geometry with the differences? Can that mess with the distances too then? Could that make things closer than we think they are because we're pushing them farther out to make them stationary?
Yes, exactly. That's the thing. They have been forced to postulate that the stars are extremely far away.
Yeah, and if I may continue, Simon, I mean, so in the 16th century, this was what they said. They didn't attack this. So they said, well, the stars can be absurdly large. I mean, you can't say how big stars God can make.
And absurdly far.
Yeah, because exactly. Because if they are so big, then they have to be insanely far away to be as small as they appear to us. Yeah, but then something new came up in the 18th century, and that was that they found parallax, annual star parallax. They were able to detect a small motion during the course of a year in the stars. And that became the revival, so to speak, of the Copernican model, because then they said, the stars don't have to be extremely large, because we actually see that they move a little bit in relation to each other. But the problem was, and that was we talked about that in the last podcast we did, the problem is that this parallax can only be positive, and it can't be negative. And could you explain that a bit further, Simon? Why and how this is such a problem? Because we don't have only positive parallax. Did we lose Simon?
You're
Simon's
muted.
Muted, yeah.
Oh, he's muted. Yeah, okay.
Oh, sorry. Here I am again. I'm back. Okay. So yes, well, the question of negative and positive parallax is extremely important, because we do have all the tables, all the official tables have like half of the stellar parallaxes are positive and the other half is negative. The negative parallaxes are impossible. Why is that? Because you have to understand what that means. It means that Earth would be going in the opposite direction. To have a negative stellar parallax, it means that Earth would be going backwards. And that, of course, doesn't happen. So, yes, Patrik, bring up this, yeah. The thing is, since we are moving very slowly, for years and years, almost on a straight line, we can see stars on both sides of our Earth as we go from left to right here on the screen. Okay, here we go. So this is a conceptual graphic I did, which is a Copernican. The Copernicans say that blue car is the Earth going around the sun. Okay, so if
that's
that
Elon's
were true,
Tesla.
Yeah, it looks like a Tesla. If that were true, if we at midnight every day we look out our right-hand window, we will see the stars, and in the left-hand window we will always see the sun. Left-hand window always day, right-hand window always night. Okay. So the parallaxes of nearby stars, which are the ones that we measure, we measure the nearby stars against the furthest distant stars, and so to calculate how far away they are. Well, if the Copernican system were true and we were going around the sun like this, we could only see positive stellar parallax all the time. We could never see negative parallax. But now you can scroll down, Patrik, and show why we do see half of the nearby stars moving positive and the other negative. More down. You can go to this.
Maybe now would be a good time to tell people where they can find the book.
Yeah.
Yes, go to Tychos.space. There you will find both Tychosium. Tychos.space.
So this is the answer to this question. This graphic alone explains it all. Because I have Joe and Jim here. Joe is on one side of the Earth, looking at the stars over several years. And Jim is on the other side, looking at the other quadrant of the stars. And so Joe will see the stars he's measuring going from left to right. I mean, he will see negative parallax, whereas Jim, on the other side, will see the opposite. He will see positive parallax, which means that the stars he will be measuring will be seemingly moving the other way, because we are going on a straight line. And then, even more important, you see to the left and to the right on the graphic, 23% assumed zero parallax, and the other side 23%, which is almost 50%. That is because in the tables they have almost 50% of stars that have no parallax. Why is that? Well, that's because if we move against a nearby star, it will have no parallax, because it's like you were driving a car, looking at a tree in front of the road, and behind the road there is a forest. Well, that tree will always stay immobile. It will not move sideways because you're moving towards it. Or if you look in your backhand window, in your rear window, the same will happen. A tree which is standing on the road and with the forest behind it will not move sideways, because that's perspective for you. So all this data they have in the this is the data they have, NASA and ESA have in their tables of star parallaxes. They are distributed in this way: 25 negative, 29 positive, and then almost 50 zero. And the Tychos explains it. And this can't be explained otherwise.
No, so I mean, the thing here is that positive parallax, if we were to find only positive parallax, that would have confirmed a heliocentric model, because there can only be positive parallax in a heliocentric model, positive annual parallax.
Yes.
But the thing is that we've not only found positive parallax, we have found negative parallax and also a lot of non-parallax.
50% almost.
So I guess, so does that mean that in the Copernican model, in the heliocentric model, there would be some parallax maybe, but you would always have to see it during the day?
Well,
No,
yeah.
No, I'm not sure.
It's something you really have to wrap your head around, Darren. It's it's the Copernican idea that we are going around the sun is absurd if we have different negative and positive parallaxes. It cannot happen, simply. So maybe your question is, how do they explain away the negative parallaxes?
Yeah, that's...
Well, I'll tell you how. They say that, that's just a kind of, it's because the parallaxes are so small and even smaller than the margin of error we have calculated to have. And therefore, under a bell curve calculation, we would expect to have many, many negative parallaxes. But they are absurd. They absolutely admit that negative parallaxes cannot exist. And they have admitted this since the 17th century, because that's when they started to see negative parallax. In fact, Bessel, the guy who first found a parallax of a star, he first saw a negative parallax of that star. And then, now I've seen a positive. Because it depends on when you look. It depends on the time window that you choose to look at that star. And it can have either negative or positive. In Tychos, this becomes clear. It depends on because they usually measure this parallax under 6 months period, okay? But it depends if it's the period that goes from March to September or from September to March. So it is very complicated, but there has been so much controversy with even modern, the biggest observatories in America in the 60s, they were all arguing about how come we all see different parallaxes for the same stars? How come we don't agree, Some see positive and some see negative. Because that's also, a complication of this whole affair. It also depends on what time window you use to measure that parallax. So it can be reverted. So they have been confused all the time because they always believe that we go around the sun.
And then instead of changing their model, they just make things fit. I mean, they really just make up stuff to make it fit.
Exactly. Exactly.
So the heliocentric model that it's really a mystery, but I would say it's because of extreme confirmation bias, and I don't know why it's so, but I mean, because if you look at this picture, you see here that if the parallax is a result of Earth's motion around the sun, then it makes sense, doesn't it, that it needs to oscillate during 6 months, right? If Earth is moving like this and then going backwards, the parallax would need to oscillate during 6 months. But it doesn't. They've never found parallax that actually is moving back and forth during 6 months. And that was a problem. But that was something that Bradley explained or solved. And that is a very famous dogma, I would call it. And that is the aberration of light. Because he said, well, we are moving like this in 6 months, but because the light is drifting in some mysterious way, we are not seeing this oscillation during a period of 6 months, but it's what he had observed was it 4 months and 8 months, Simon?
Yes, no, it was 3 or 9 months, and I explained that in the book as well.
Yeah, you explained so brilliantly why Bradley saw what he saw. And that is, what's the name of that chapter?
It is, which chapter is it now? It's, which one is it? Yeah, deconstructing Bradley and Einstein. Deconstructing Bradley and Einstein, yeah. Here we go. These two guys are the ones who have upheld the idea of heliocentrism. They've been really, really good at maintaining the impending collapse of the Copernican system, because Bradley came up with this absurd stellar aberration theory, and Einstein came up with all kinds of other stuff, which, well, we don't have time here. But yeah, they were probably, they had their role was to uphold the Copernican system, which for some reason they want to uphold. If you scroll down now, Patrik.
Yes.
Since you mentioned because Bradley had been looking at a star above his house for a year and more, several years, and he wondered why the star it was a star in the north, Draconis, and he looked at it, and then it really behaved strangely. He didn't understand why. It was the maximum elongation from the point he was looking happened in 9 months, whereas he was expecting it to happen in 6 months. And this is illustrated here. You need time to wrap your head around these graphics I've done. But this is what we're seeing here. What is this white line in these graphics? The white line, this trochoidal line, is the trace that a man will do. A man in London over a year will actually do this path. And therefore, if he's looking for a full year in a star, he will see the star moving in such way. And that's what Bradley saw, but he didn't know about this. Why is this white line there? Why does it exist? It exists because we are going slowly forward, as I posit in my system, and therefore a man and Earth rotates in the meanwhile. And I'll tell you, this white line is exactly what any person will do. Any person standing in the same place for a year with a telescope will go around this white line, this trochoid, this loop.
And that's just based on the tilt and the rotation of the Earth?
It's based on the motion of the Earth. It's just like, the retrograde motions we saw before with Mars, because we are rotating around our center of the Earth, and we are also moving from left to right here. Okay.
So we are spinning like this, while we are moving slowly in 1 mile.
1 mile,
direction.
1 mile per hour.
Yeah, so
right.
Bradley's
So I guess
observation,
in 24 hours, you're moving 30, 40 kilometers or something like that. The Earth is...
but all the dots here, all the different dots on the white line, they are, on the same day of the same of each month. So it starts like March 21, and then go April 21, May 21, June 21, July 21. So you have to understand that. And so that is why this explains exactly what Bradley writes in his book. He was baffled. He didn't understand. But then he said, "Yeah, one day I was on a boat and I saw a flag in the wind, and then I came up with this idea that it must be because of this and that." But he just made up something to explain this phenomena. But it's not. It's nature. It's not a phenomena. It's absolutely natural.
Yeah. So I mean, in a nutshell, and it takes a while to wrap your head around this. At least it did for me. But
yes,
Bradley's observations becomes yet another confirmation of the Tychos model. Because if you assume these motions that Simon suggests, then it's what Bradley saw is explainable in this way. But he found another explanation. That was, the light is drifting, or
Yeah, it's like a rain falling
that's
on you.
so funny, and you can read about it. This because
Yeah.
that stirred a controversy. Because there was another British astronomer who's called Airy, and he disproved Bradley's claims that lights drift. It's called Airy's failure.
Yeah.
So yeah, it's so fascinating.
It's an incredible story.
I have a quick question about the speed. Is it possible that we're slowly speeding up or slowing down? Like, were we ever at an exact mile? Is that why a mile per hour is a thing? Because it feels like a sacred measurement in a way based on natural rhythms. Was it ever exactly that, and now we're slowing down or speeding up, or
no, we are never slowing down or speeding up, and that's another question I broach in the book. They think we always hear about stories about the Earth slowing down or the Moon speeding up, and these are just illusions that are created by the fact that they don't know how our system is configured. The system is extremely stable, and these small apparent accelerations are just illusions, and that's explained in my book. I really can't explain it perfectly here.
Yeah, that's okay. Darren, do we have any questions from the chat or anything, Darren?
I haven't been watching the chat. Why don't you? I'll check. You do something.
Well, let's go back to Tychosium for a bit and see if there's anything else. And
I would like to say one thing.
Sure.
We haven't been talking about.
Okay.
It's so we talked about the distance of the stars, right? Which are incredibly distant according to official astronomy. The reason why. What does the Tycho say? Well, the stars are much, much closer. And how can I say that? Well, this is because maybe Patrik can bring up, let's see now, what can he bring up? Maybe Patrik, you could bring up chapter 23.
Yes.
Right? And scroll down. Now, just to explain how they have calculated that the stars are that far away. Down.
Yes.
Scroll down. Here, this one.
This one, yeah.
This one, yeah.
Yeah.
How star distances are currently measured. This is how they measure the distance of the stars, okay? A nearby star, they want to know how that nearby star is here in the middle, how far it is from Earth. So since they believe that Earth is going around the sun, they say, okay, in 6 months, Earth will move sideways by 299 million kilometers, or about 300 million kilometers, okay? You see?
Yes.
An astronomical unit?
Yeah,
What?
1 astronomical unit.
Is that what that is?
Well, actually, it's two astronomical units.
Yeah.
1 plus 1.
Yeah.
So they say, okay, we wait for 6 months. We take a first measure. We take a first picture of that star in June, and then we take another in December. And then they assume that we have then moved by 300 million kilometers. And so they do a little trigonometry, and they say, oh, well, that star is really far away. It's so and so. In the Tychos, however, Earth in 6 months only moves by 7,018 kilometers. Well, 7,018 kilometers, the distance that the Earth moves in 6 months is 42,000 times less than 300 million kilometers. That's why I dare say that the stars are 42,000 times closer than currently believed, which is not anything crazy, because that would bring our nearmost star Proxima. Proxima is our nearest star. That will bring Proxima at about 6.5 astronomical units, which is pretty far away. But 6.5 astronomical units is between Saturn and Jupiter or something. Yeah, between Saturn and Jupiter. But that star, the Proxima, is not on the same plane of our system. It's 60 degrees down. So it's probably a much smaller object, and it has a companion as well, and so has its parents, Alpha Centauri A and B. I mean, they are all binary stars,
Oh, so if you were to rotate that our system down, it would intersect with that?
They are 60 degrees away from our plane, so they wouldn't disturb us at all, even if they're that close. But then all the rest of the stars are much further, so most of the stars are certainly further away than Saturn. Okay, almost all of them, but some, and that makes statistical sense. At least some stars should be maybe closer than Saturn, but that's not crazy to say. And yeah, maybe they're not really big stars. They're much smaller than we think. So that's it. The stars are 42,633 times closer than currently believed, and that's what I'm stating here.
So may I try to explain this in another way, because the thing is, the way they calculate the distance to the stars is using triangulation. You have a triangle, and one side of the triangle, and two angles, and then you can calculate the size of it. So if you have a 90 degree, you have one angle, and then you have this angle, and you have the base. So the problem is, if you assume that this base is about 300 million kilometers, while it is in fact only 7,000 kilometers about, then you make a very bad calculation.
Well, not to mention by your own calculations, the failure rate is too big for us to say anything. It's fucking crazy. It's just like, well, we're not accurate enough to say, so we're just guessing.
Well, yeah. I would, well, we are kind of guessing, but I think I happen to think geometry works very well, and if we only have the right numbers, if we only use the right numbers and angles, we can figure out the distance by means of triangulation. But the problem here is if you assume that a number is not what it is, then it becomes
well. Not only that, the triangle's always going in the same direction now. It's not going back and forth. It's always going one way, except for that 26,000 years. It's going back and forth in 26,000 years. Maybe you could do it over in 13,000 years. You could make some observations.
Yeah. And you still have the problem, and you bring up this in the book as well. When astronomers started to look at parallaxes, it became quite confusing because they got different parallaxes depending on when they measured. Yeah. And this is still going on. So some astronomers claim that the distance to the Polaris is only 2/3 of what other astronomers say, or how much is it? You talk about this.
Yeah. Very recently, they have shortened the distance to Polaris by 1/3.
That's a big variance, 30%.
33% closer. Yeah. So people think that astronomy is all settled, and they all know everything, and they are so accurate. But if you look at if you go and read what they are talking about, they are always arguing. And there is controversies all the time. And the funniest thing I found from April 2022 is from Science News, and they are saying I mean, listen to this. They are saying that new studies have determined that binary stars keep masquerading as black holes, because they found that binary stars, these two, a big star and a small star, they can sometimes be mistaken for black holes, because if one of the stars rotates very quickly, it will be kind of invisible and they can't see the spectra of that star, and they assume then that it's a black hole. This is very recent. This is from April 2022. And so here we go again. They are discovering more and more binary stars. They said, in that article, they said, well, we found 2 or 3 black holes, but we had to admit that they were not black holes. They were binary stars.
Wow.
Yeah.
So is that what the Berry Center is? I mean, a black hole?
The black holes are illusions. I mean, even dark matter was discussed in the 19th century. Dark matter was something that was supposed to exist. They couldn't figure out because their calculations wouldn't match with Newtonian gravitational theory, and so dark matter was, pulled out of a hat. But then we had the great stellar statistician Jacobus Kapteyn, Dutch guy, who was a master of statistics of stellar distribution. He said that, well, I can see this. He came up with a theory which is called star streaming, and he was saying that one part of the stars are going in one way and the other part of the stars are going the other way. Well, that's what we would expect in the Tychos, isn't it? Because if you can see the stars on both sides of Earth, at night, then it would seem like the stars are going in 2 different directions. And so he said that, he said that this must be the case. The stars are going in 2 different directions. And he finished his in the last part of his life. He said that if it turns out that all stars are binary, then we don't need to evoke dark matter.
Oh, that's interesting.
Yeah.
Wow.
And dark matter doesn't exist.
When was that? In the 1800s?
Here we go. Thanks,
1850s?
Patrik.
Yeah.
Let's see now. In 1851.
Oh, he was born in 1851.
He was born in 1850. Early 20th century, actually.
Oh, that's so fascinating.
Yeah.
And now they're also admitting. So this is another one of those examples where it just doesn't. The science narrative won't catch up to the actual paradigm, because they're admitting that 80% of them are binary, yet they're not saying all, which would mean there's no dark matter,
and
or dark energy.
Yeah, Graham, and this Jacobus Kapteyn, who was extremely eminent and respected, he's been buried now under, he's put in the dustbin of history. No one talks about him anymore. But he was one of the best, and everyone was really, really, attached to his mouth, because he was apparently, they described him as an astronomer without a telescope, but he earned all the telescopes of the world, because he took data from all the telescopes and made, comparisons between them. So he was a really big ass guy. I mean, he was one of the best, and they are now ignoring him. He's who knows? Jacobus Kapteyn? No one. But go and read his research, which I've done, and you'll see that, of course, he was also Copernican, so he didn't understand his own findings. But he concluded that there were 2 star streams, one going one way and the other the opposite. And this is exactly what you would expect in a Tychos paradigm. You see what I mean? There can't be two blocks of stars going. It's just because we are going on a straight line, kind of. For 100 years, we'll be doing kind of a straight line. and on both sides we'll see stars going one way and the other. Negative and positive parallax. That's the whole thing.
At least over our short lifetimes.
Yeah. Yeah, we have 2 short lifetimes.
Well, I don't have anything super intelligent from the chats. We got some flat Earth stuff. I don't think we're going to entertain that here today.
Please.
Okay, here's one. And we did kind of explain this, but we'll do it anyway. From Old Shoe. This model shows Venus and Mars coming very close to the Earth. Is this anywhere true to scale?
Yes, it's perfectly to scale. The only thing that's not to scale, and I have to say this, in the Tychosium is the size of our moon's orbits, because we had to do it bigger, otherwise it would not be visible, graphically.
No, it goes so close. Yeah.
The only thing
the moons are much closer, right? Yeah.
The moon's orbits, the diameter here on the Tycho is 39 times bigger than reality, but all the rest is to scale. I mean,
does that include Venus?
The
and
size of the
Mercury,
sun. The size of the sun is not to scale either, because it's certainly bigger than that.
So,
but all the
when
distances.
you say moons, does that include Venus and Mercury as moons? Then, so those would be tighter to the sun?
They are to scale. Their orbits,
Their orbits
are to scale. The orbit of the moon,
our moon only,
not to scale, because it would have been too small to be visible graphically. So I made it 39 times bigger for some reason I explained. But the rest is all to scale. It's just the diameter of our moon's orbits, which is made bigger to be visible.
We got another one here that asks if we should be counting our birthdays differently. Someone's trying to be younger with your model, I think.
Well, the thing is, we also have to, revise maybe, which sign we were born in, because we move one sign every 2,112 years. We move from one sign to another. Maybe you can open the.
Yeah, that is also one thing. We have actually have a zodiac now in the
right.
Yeah. So I mean, there are lots of hidden things here to be able to understand how the precession works and everything. Go ahead, Simon.
No, I just wanted to say that we in our generation, like I would be Aquarius, right? But I was actually born when the sun was in Capricorn. So this is because we are moving around our PVP orbits, and everyone has has their zodiacal sign offset by 1.
Forward or backward? Can they figure it out? Maybe it'll make more sense for some people. Maybe it'll make less sense.
Forward.
Yes,
Forward, I'd say.
ruin some people's lives.
So I would be Capricorn, but I don't feel like a Capricorn. I feel like an Aquarius. But I mean, this is just, this is astrology, and I don't go into this field.
Do you think there was a time when the ancients understood your concept better than our modern day sort of people, like before Copernicus and before Tychos? And do you think they understood it at some point?
I have a strong feeling that they knew much more than we ever could imagine. Yes, absolutely. Yeah. Absolutely. Because the Maya, I mean, I was even helped by some old Maya papers that I read, and they knew about the exact 29.22 day revolution of the moon. Yeah. Which is very important in my Tychos. And they knew about the exact, they knew about that Mars had 2 different synodic periods, 707 days and 546.
Yeah, there you go. Wow.
They knew that. So, so where did I read it? I read it on a modern paper, which explain these things about the Mayas, but they don't even conclude anything about it. They don't connect. They, these intelligent people should have said, "Why? Wow! Wait, how is this possible? How is this even possible that Mars can have two different synodic periods, 707 days and 546?" So the mystery I still haven't solved is why haven't those people reacted upon this ancient knowledge? It's really amazing. They should have. And it becomes a bit embarrassing, to say this, because who am I? Am I, the only one who's found this? No, I've found other people who are also discussing about the problems with the Copernican system, but someone had to finally. Well, that's where
write it all down.
That's where I get boastful. I actually found the solution. I actually found this last piece of the puzzle. And that's the PVP orbits, really.
Yeah, and it explains the precession and the precession of the equinoxes. And may I try to explain this using the Tychosium, what the precession of the equinoxes is and why we are moving from what's it called in English, Pisces to Aquarius. Pisces. Yeah, thank you, Pisces. Because we are. It's that song, the age of the Aquarius. So what does that mean? Well, it works like this: that every vernal equinox. And what is a vernal equinox? Well, it's when the equator intersects the ecliptic. Mm-hmm. So you see here. In 2001, we had the vernal equinox at the 21st of Mars. So when the sun intersects this line, they check which star it's in front of. And we have these star signs. And this is the Pisces. And what you see down here is a fish. So that makes sense that it's the Pisces. And if we go up, and I brought in these star signs. We need a better way to illustrate this, and we will work on this in the upcoming Tychosium. But if we look at Aquarius, then we see someone pouring water here. So this is the age of Aquarius. And what is happening then? Well, we are now in the borderline of the age of Pisces and Aquarius. So if I move the Tychosium 1 year forward now, you will see here that, let's turn off the trace. Let's do 10 years.
We have already entered Aquarius, according to my little calculation.
Yeah, but if you just let me... Go ahead there. You will see this green line, which represents this line moves slightly. So we're entering the age of Aquarius, and now now we have moved forward to the year 2109. So, but there is no consensus on when we are in the age of Aquarius. But as you said, Simon, you think we are already there.
No, Patrik, I just said this. I mean, I'm not sure about this. This is just speculation. But the other day, I was curious about that, and I tested the Tychosium, not like you're doing now, but it looks like. In 2012, you remember 2012 was important date where the Maya was saying that there would be some big change, and it looks like in 2012 we started going into that little piece of cake that is Aquarius, but it's those 12 divisions are not exact, so it's a bit up in the air really but I think we're probably into Aquarius now, but it doesn't really matter. You know, these 12 cake pieces that they've divided our celestial sphere in are not exact, because they are based on. I mean, it's not exactly 12 pieces. They are these various constellations are not symmetrical, you know.
No.
So it's hard to say.
But when you plugged in 2012, it lined up exactly with the line there.
Yeah, it did actually.
Yeah,
I agree.
It lined up exactly when you plugged in 2012.
Yeah, you
So,
see,
I mean,
that's what
it. Maybe that's the exact trend. Well, as close as
that's
you're
what
going
I
to get to the
tried the
transition
other day.
point, yeah.
That's when we made
That's
the
what-
YouTube channel, December 21st, 2012.
Yeah.
Just saying. I think maybe the Facebook too, which I'm currently suspended from.
So, what do you say, guys?
I have one more question. Let's go to
ahead.
one more question from the chats from our handler James Nation. As the sun moves around the galaxy, is there any gravitational changes expected? Is the sun's orbit the same and consistent, or is everything too far away to affect the sun's orbit?
Shall I take this, Patrik, or you?
Yeah, I have no answer. So go ahead.
No, I only have one thing to say about the stability. Everything I've been, day by day now for almost 10 years, I've been amazed at the stability of the system. Everything is extremely stable, and all the small variances and changes that they have been debating about, astronomers, for many years, I have actually solved them. There were no variances. Jupiter and Saturn apparently didn't conjunct as they expected, and all these things are just made or just caused by the fact that they don't know about the PVP orbit. They don't know that we are moving slowly around an orbit. So these small discrepancies that we were discussing, the fact that Jupiter and Saturn weren't aligning every 60 years as they were expecting was a drama for them. They were saying that Jupiter would then inevitably crash into the sun, and Saturn would go out into outer space and disappear. That was the discussion in the 19th century. But then I show in one single graphic why this discrepancy happens. It's just a matter of perspective. Because over a certain 60-year period on one side of Earth and another 60-year period on the other side, there will be a little discrepancy because we are moving slowly around our orbit. So I really think the stability of this system is amazing, and I don't believe in all these theories of the moon was created by a big thing crashing into Earth, and those impact theories and crazy stuff that they are many serious books are writing about. It's an incredibly calm and tranquil system, and nothing ever changes, at least in this time span that we know of.
And there's nothing special about Earth in this way either, right? It's just more of a coincidence. Like, it doesn't seem like it has to be this way. It's just that we are in the middle, right? Is that what you think? And then Patrik, before you wanted to finish the procession with this view, right? As well?
Yeah. And I just want to throw in a plug as well for, and you were familiar with David Matheson, and and this book, the Star Constellations, because I was so amazed when I started to look at this. I mean, everyone interested in stargazing should look up David Matheson and the constellations, because when you start to look at the constellations as they are drawn in this alternative way, but I would say it's really in a way it starts to make sense because you can see the actual figures. I mean, here you see someone pouring water, the Aquarius, a fish. And,
show it with your mouse. Show it with your mouse properly.
Yeah.
The man.
Then we have the Aquarius. Yeah. So a guy pouring water.
Oh yeah.
Yeah, and here we have Pisces. Yeah, a fish down there. So because if you look at the official constellations, they don't show anything. They don't make sense.
They've changed them.
Yeah, they have changed them. Yeah, and I think it's intentional. They don't want us to see these things and understand. I mean, here we have the Leo. Yeah, there is a lion. And this is, and let me go over as well to and talk a bit about the new Tychosium I'm working on, because we need to do a lot of things to show the model better. And one very important thing that I'm working on, and now we're going back to the new Tychosium that I'm working on, is that of course we need to see things from an earthly perspective. I mean, we are looking on everything from outer space now, but of course we need to be able to look at things from Earth, and it's a bit tricky, but I'm working on it. And the amazing thing with this model and simulator is that here we can do this. We can transform in the same geometrical space. We can go from outside and down to Earth and look at things from Earth, because this is what no other planetarium can do.
No other.
We can look at stellarium, and we can see things from an Earth-centric, and we can look at the Copernican orrery, like JS orrery, and we can see things. But they can't bring in the stars and the planetary motion in the same model, and the problem was what I demonstrated in the Tychosium before, because if you had the sun in the middle, then it becomes a problem with the stars, because then
to simplify, in other words, sorry if I interrupt, there is no existing simulator of a solar system that can jump from one view to the other seamlessly, seamlessly. So this will be, when Patrik is ready with this, I'm absolutely confident that this will be the first ever simulator which can do that.
Yeah.
Okay.
So that's what I'm working on. And if let's turn off the arrows here. So here we have a checkbox, planet camera. And so if I check this, we will fly into Earth like this. And you see here is the placement of the camera, and boom, we are in an Earth-centric view. But I'm still, there's a lot of work to do. We need to scale down the planets and make everything work. But it's starting to work, so we will see things from an earthly perspective. And if it's
so,
and
awesome.
the thing is, I need to reset it now because it does. But the way it works, if we can put on this show helper here. So this is what the earthly camera sees. Okay, so and I can change latitude and longitude, move it around on Earth. And what I need to figure out as well is, of course, to do this with a split screen.
Yeah.
So
you can be on Earth at the same time.
You can see things, how it looks on Earth on one side of the simulator, and then you can see it from the bird eye view.
The God's eye.
Yeah. And I mean, this is amazing because I'm working with a 3D framework called 3GS, and I mean, you can just do this if you have the correct geometrical configuration of our solar system. It's not it's not hard to do, actually. So yeah.
Well, it's only possible to do.
Too hard for me to do.
yeah, it's still a lot of hard work, and one thing that I'm doing here as well is that the thing, with the Tychosium is that it's working. It's great, the original Tychosium. But if you go and look at the code, if we go here and look at the code, it's been what's it called, ad hoc work. It's very messy and hard to understand, because I've been working on it for years, and just added things.
Adding, yeah.
Yeah. You guys work with construction, and you know how this works. You just patch things up. So, but the thing is, with this new Tychosium I'm working on, I'm doing it very nicely from the ground up in a modern framework that's called React. That is a very common way to do web applications, and I've used the abstractions in a good way that I'm proud of. So this is the actual system here, and it's so simple because you have a group of objects, and you have the barycenter, and its children is the Earth, and then you have the moon deference, and the moon is attached. So everything is very neat and well done in this new Tychosium that I'm working on.
I just want to say something. I think you guys, Graham and Darren, you can probably imagine how lucky I feel to have met Patrik.
I feel the same way.
Where would I be today if I only had put this on paper and there was no Tychosium? Because that's what I did for several years. I was just making on paper all these calculations, and on my side, I would say that I did. Wouldn't you agree, Patrik, that the data I gave you was correct? I mean, I gave you the numbers of how to make this. Numbers of all the planetary motions, but
yeah,
I was completely incapable to put it into such a system.
No, and
I feel
what's
so lucky.
And I have to admit, when I started with this, helping you out with this, I was anticipating somewhere where we figured out, no, this doesn't work.
Yeah. Yeah. Somewhere. Something must
never happened.
No, it never happened.
It never happened.
No, and this has been going on for a long time now. And the good thing also is that I can reuse a lot of code in when I'm building this new one, because there's been a lot of hard work, for example, to get the calendar working, because that's something very complicated, human dates and the things we have done. Because, for example, in the 15th century or the 16th century, we moved from one type of calendar to another type of calendar, from the Julian calendar to the Gregorian calendar.
Right.
So we actually have a few dates that is not non-existent. So if I go, if
like 11 days.
Yeah. 11 days. So if I type 1582, 1582, 10.
You know that, guys, don't you? That
05?
they changed the calendar in 1582.
Oh.
You know where they changed it, guys?
Where or why?
Where? They had the big reunion with the big astronomers of the world at like stone throw from my house where I live now.
No way.
Yeah, in Villa Mondragone, which we visited with Patrik a few years ago. It's a huge villa where they invited all the biggest astronomers of the world, with the Pope, who wanted to fix the problem that Easter wasn't, falling on the proper date. It had been drifting by 10 or 11 days. So that's why we have, in the whole world now, we have the Gregorian calendar. And that was made in 1582.
Yeah, so the thing is, if you go here to what is it, October 1582.
Yeah.
And we go to the 1st of October, that works. The 2nd works, the 3rd works, the 4th works, but the 5th, you see it jump back, because these days don't exist.
Right.
So it won't accept them. It will just jump back to whatever was there before.
Right.
I remember that day.
But if I go to 15th, then it works again. And just to show you here some of the hard work. So if you go and look at, where is that? Time and date functions, Here you have some of the code and calculations needed to figure this stuff out, to transfer calendar date to actual celestial position or to the position in the model. So it's been quite some work here, but it's working very well now, and I really like this type of date. Well, it's a Julian day. That's an astronomical date, and
it's used officially as well. It's
I said it was an astronomical.
Oh, that's
date.
interesting. Yeah, so that's strictly just based on our rotations in the planets, not any sort of.
No, it's just number of days from. If I say Julian day 0, that will be 4712 BC.
Yeah.
That's the day 0. So, and if we go to the year 2000, or remove the minus here, so we're about. So it's just they're just counting the days, so there's no leap days or anything. It's just a number.
Can I say just some funny thing I did the other day?
Yeah.
I went back to I went to the NASA site, which deals with the solar eclipses. Okay, and I was curious to see what is the oldest solar eclipse to have listed here. Well, one of the oldest was -399 on some dates, maybe 6 December or something. So 399 before Christ. Okay, BC. I went to the Tychosium, and bang, there was the moon, exactly in front of the sun. There was a solar eclipse in 399 before Christ, and our Tychosium checks out with that. And you have no idea how many other dates have checked for all the planets. And sometimes it could be a few minutes wrong, but really everything works in an incredibly accurate manner, in the sense that all the, because there are some really credible documents, of some important events in the past. And I always go and check them on the Tychosium, and they always check up now. They didn't in the beginning, but now we have refined the Tychosium, and it's absolutely astonishing how accurate it is. And what I mean by accurate, I mean that it does check out with ancient books and observations. Solar eclipses, the Venus passages in front of the disk of the sun, which are very rare, they all check out. All the Mercury passages in front of the disk of the sun, they all check out. I mean, what more do you need?
Where can our listeners find all this stuff, and is there a way to support your guys' work?
Well,
Yes, you will find us at Tychos.space, and you can donate to Simon. If you go to book Tychos.space, there is a way to donate, and
would be nice.
that is much appreciated because this is done, of course, without any funding.
Zero
yet.
funding.
Yeah. So, but I mean, this is just a work of joy, and it's I'm a developer, and I like to build things, and this is the most interesting project I've ever encountered. And another thing I'm working on in the new Tychosium is to make things a bit more visually appealing. So you see here we have a little clouds moving around here, and I should add something that's called a bump map, so you have a bit of texture on the Earth. And another thing we will be able to do is someone was mentioning eclipses.
Mm-hmm.
So these type of 3D engines, they support shadows. So I mean, we could do actual physical eclipses.
Cool.
Yeah.
But then we need to set, of course, the moon and the sun and the Earth to a correct scale before we try to cast shadows.
Yes, it's a scale. Yeah. But even if the scale is wrong, I've been checking some of the shadows, and they kind of check out. Like if there was a solar eclipse in Australia, that would be the shadow would hit Australia, but not quite because the proportion of the moon's orbit is not to scale.
Yeah, exactly. The moon's orbit is too wide at the moment, because otherwise we wouldn't see it.
But if we can get it to scale somehow, I think it will be exact. It will check out with all the, you can go on the internet and find the exact passages of the solar eclipses, right, on the surface of the Earth. They go like maybe some place in the Pacific or over Europe, and roughly they check out now, but not quite because the proportion, the scale of the moon's orbit is not the scale. It's not okay.
So just to reiterate for everybody too, that this model is available online for anybody for free, just to go play around with it. I mean, you can go in there, you can run it at different speeds with different planets, different tracings, all the different positions and help tools and all that. So go ahead and play around with it, everybody.
Yes, please
great.
do. It's funnier than playing video games, guys. Because it's a reality, I think.
So this Tychosium is available, but not the one I'm working on, and it's not in presentable condition yet, but it's going to be. But we are planning a lot of new features, and one thing is that it's built in a way so everything is dynamic, and that will be a joy for Simon when he adjusts. So you can do everything in real time. Adjust the sizes of orbits and stuff.
Wonderful.
But it needs work. But yeah.
Wonderful, Patrik. Wonderful.
Right on, guys. Well, thanks for staying up late and doing this with us again. I think it'll be one of our more popular YouTube videos. Anything else you want to plug before we wrap it up?
Oh, just that we have Tychos.space. That's where you want to go. You can read the whole book. It's 32 chapters. Because you really need to read the book to get into the whole concept, and then ts.tychos.space. That's where you can find this simulator and play with it. Wanted to repeat that because we have no publicity machine. We really hope that at least the one that listen to us will do the effort to read the book and look at the Tychosium simulation. That's all.
Totally.
Yeah, and my final words is that I like to read comments and reactions on this work, and I read some of the YouTube comments on the last podcast we did, and there was one comment I think it's so telling that someone said, "This needs to be disproved quickly by authorities." And well, I think you need to look at it yourself and think about it for yourself, what makes sense, because that's the problem. That's what we do. We find someone who tells us how things are, and that's what I would say what that has led to this situation where human culture or human civilization, we have actually drifted very, very far from reality. And what is actually true and confirmable, and we have drifted further and further away from actual science, like actual geometry, actual physics. So you need to do that work yourself. You can't find someone who does it for you. You need to do the work. You need to read Simon's book and make up your own mind and try to understand it with the help of the Tychos. So you know, it can be very startling to find that big questions like this can actually be have to be asked, but it's also very rewarding if you do it, because you get a good perspective of things and the world. And as they say, perspective is everything. It's very important to have a good perspective. And I would say this work that Simon has done with my help for over almost a decade now is very helpful in doing that. So
you guys have done
thank you for listening, and thank you for having us.
Yeah,
you guys have done
a
great job of putting it across. The video is even better than the podcast. So I mean, I'm happy when you guys do launch that Tychos 2, let us know, and we'll make sure we let everybody that listens to us know. And I mean, thanks guys. I think it's been great. So that's Tychos.space. To check out all that stuff. You guys know where to find all our stuff over at Grimerica.ca. Big thanks, Simon and Patrik. Thank you again, and you did a wonderful job.
Thank you.
Thank you so much. Thanks, guys.